So this is how it's all related. If I just play an A note, this has a frequency of 440 hertz. But since it's all related, if I just change the length of the string, that'll change the frequency and thereby change the pitch. So and so on and so on.
So, reed instruments operate like stringed instruments, but not in the same manner exactly. Reed instruments only make odd-numbered harmonics. Each harmonic is a specific note. So, that's really main a difference. And reed instruments have octave keys, which make your notes go up one octave higher, which is eight steps above that note that you just played. So let's say this A here, which I'm going to play right now, is my regular A. But with the octave key, it raises it up 8 steps. It's the exact same note, just raised up.
The equation for wavelength speed is wavelength speed equals frequency times wavelength. Now, in order to find the wavelength, you have to do a different equation. The wavelength equals 2 times the length. So, if the length of a cello string is 0.698 meters, you multiply that by 2, and the wavelength will be 1.396. Now, say an A note, an average A note on the cello is 440 hertz. That's its frequency. So, you plug it back into the first equation, and 444 times 1.396 equals the wavelength speed of 614.24. Now, if you put in the hertz for a C note, that's 262 hertz. Then 262 times 1.396 for the wavelength equals a wavelength speed of 365.752. Sound waves produced by an object at rest will have the same frequencies no matter where you stand. But sound waves of an object in motion's frequencies will differ upon where you stand. If the object is approaching you, then the waves will be closer together and produce a higher pitched sound. If it is moving away, then the sound waves will be spread apart more. An object moving at the speed of sound will always be at the leading edge of the sound waves it produces, and an object moving faster than the speed of sound will reach you before you actually hear it. The resulting compressed sound waves will then cause a sonic boom.
Amplitude is the degree of change in atmospheric pressure caused by sound waves. The distance of the curve is the amplitude itself. Depending on the time between vibrations, the antinodes are either close together or far apart. The distance between the two peaks of the antinodes determines the frequency of the wave. In a vibrational wave, there are nodes and antinodes. Nodes remain stationary during a vibration, and antinodes move in a parabolic manner, vibrating back and forth between a large upward displacement to a large downward displacement. Nodes and antinodes alternate positions in a standing wave pattern.
But we all know why he came. So
Swag Team! Yo, Dark Knight and Aladdin all up in this piece. We ain't here to talk spit, not here to talk street. We were asked to teach us something and we're finna do it. We finna tell y'all about the physics of music.
Let me tell you something here about frequency. It happens when objects start to vibrate, you see. A push or a flick will cause an object to shake. Too much frequency will cause your head to ache. Sometimes can only be heard if the amplitudes of the vibration are large enough. Heard that, dudes? It's really simple, it doesn't take much to think that frequency equals speed divided by wavelength.
A wave is energy. Once it's in motion, when it moves through the air, it causes a commotion. It travels through objects like a bird through the air, transporting energy from here to there. Sound is the result of vibrating, and it uses a medium to travel, you see. When you put the two together, you create a sound wave. They push and pull on objects so that they are displaced.
Amplitude is a change of atmospheric pressure caused by sound waves using n-squares and measure, directly related to the intensity of sound. Amplitude has the power to knock you to the ground. It's also the amount of force applied over an area. We're going to say next just might scare you. To noise n-squared is all we can hear, and if I say you just must have waiting in your ear.
Doppler effect is not really hard to explain. If an object is at rest, then the sound will be playing. Once the object starts moving in and out of range, then the pitch of the noise it makes starts to change. Going Mach 1 is not an easy task. One must be at the leading edge of the sound waves they have. If it breaks the speed of sound, it'll make a sonic boom, and you won't hear the sound till it passes you.
When you feel the ground shake, it's not your imagination. The feeling you feel is called force vibration. Force vibration equals an increase in amplitude. When Joe plays the cello, he shakes the house. Dude, resonance and vibration are related to each other. When one object vibrates, so does another. When I play the very sax, people around me shake, since large vibration is the result of resonance.
Yo, listen up, cause I'm here to say how the cello and the bass and the strings come into play. When you pull a bus across the string and make a sound, it's the result of all those sound waves bouncing around. The bridge starts to shake and vibrate too, trying to produce some really nice music for you. Once the waves hit the sound waves, they get amplified, and my rhythm and the beat take you for a ride.
Instruments operate using a closed-end air column. Air can only move in one direction, up from the bottom. The air column determines the pitch of the note. This is important so you don't sound like a goat. Instruments produce vibrations on a reed, so the reed vibrates at its natural frequency. When instruments produce harmonics and type of vibrational waves, but only odd ones are produced like ones on the same line, okay?
So you might be thinking, Cudge, how does this apply to me? Well, listen up, cause it's real easy. When you're listening to all your MP3s without sound waves, that simply would not be. Jamming to your songs, getting in the zone. No frequencies to make that all monotone. Dark Knight Aladdin, that's how we do it. We love to get down with the physics of music.